Hello all, welcome to the lecture 4 of Inorganic Chemistry Group D, Analytical and Instrumental, based on Tribhuvan University, Nepal. This is Damodar Koirala. So this is our fourth lecture. In our first lecture, we did the introduction and basics on chemical analysis and titration. In our second lecture, we discussed about the redox titration and redox indicators as well. In our third lecture, we discussed about complexometric titration and precipitation titration and the reagents and indicators, complexometry indicators and adsorption indicators. And today in our fourth lecture, we'll be discussing about common organic reagents. Let's get into the syllabus and see what we have to study in details. So on this last one, uses of common organic reagents in chemical analysis, we have to discuss three of the reagents. They are DMG, Oxide, and Cupferron. So here we have to study the uses of these reagents. Now remember, this is the last lecture on the part 1. Okay, and these reagents are separated from other reagents like potassium bromate and ferric salt. What is so special about these three reagents? One of the special thing is they are organic reagents. So we are studying inorganic chemistry, or we are studying the chemical analysis of inorganic compound. However, these three are the organic reagents that will be used in chemical analysis of inorganic compound. Okay, now we are more focused on the uses of these compounds, so it is mostly theoretical. Like you have to study on your own, like what are the uses of DMG, Oxide, and Cupferron. There is very little I can help you. So in today's lecture, what I'm going to do is I'll be showing PowerPoint slides, and I'll be showing some research articles on how these chemicals are used, these reagents are used, and I'll be showing a website where one of the reagents, the information of one of the reagents is given, and also I'll be showing some part of the textbook to help you find out the information using different resources, and you can do the study on your own. Okay, now let's move into the topic. So the first topic is DMG. Here D stands for di, 2, M stands for methyl, CH3 group, and G stands for glycooxide. So here is the structure of DMG given on the slide. So there are 2 nitrogen. These 2 nitrogens are each connected to OH group, and each nitrogens are forming double bond with carbon, and 2 methyl groups are attached to that carbon, each carbon, okay, 1 to each. So this molecule is symmetric, as you can see. There is plane of symmetry in this molecule. Okay, this is the structure of DMG. So DMG is the colorless crystal with melting point of 239 degrees centigrade, and it's soluble in organic solvent and solution of alkalis. So this compound, or this chemical reagent was first suggested by L.A. Chugab in 1905 as a specific reagent for nickel analysis. So one and most useful uses of DMG is as a specific reagent for the analysis of nickel analysis. So whenever it is asked to write the uses of DMG, you must mention that it is used in nickel analysis. So how it is used with nickel analysis, or with the nickel salts, it yields a red insoluble precipitate. The precipitate, the powder is shown in the figure here of nickel dimethyl glycoximate, which is a chelate compound. So it is related to complexometric reaction. DMG is mostly used for qualitative and quantitative analysis of nickel 2 plus ion. So what is qualitative? Qualitative means it is used to determine whether or not nickel ion is present in our sample. So the answer is either yes or no. Okay, if it is present, then the answer is X, yes. And if nickel is not present, then the answer is no. That is qualitative analysis. And the quantitative analysis of nickel means if it is present, then how much of nickel 2 plus ion is present in our sample. Okay, to determine the exact figure, numbers. The answer will be in figures like 0.1 gram, 0.002 gram, something like that. Okay. So here is the reaction that shows how nickel 2 plus ion forms complex with DMG. So here's the nickel 2 plus ion, and this is DMG, and it forms the complex as shown here, which is called dimethyl glycoximate. And the color of this complex is shown here, which is red, dark red. Okay, so let's see what's going on here. In this reaction, these 4 nitrogens are pointed toward nickel. So these 4 nitrogens are from 2 DMG. Each DMG has 2 nitrogens, so 2 DMG has 4 nitrogens. And this nickel is forming bond with those 4 nitrogens. Okay, during this process, you added 2 hydroxide group and you removed 2 water molecule. Okay, so you started with 2 plus and you added 2 minus. So the overall charge on this complex is 0. As you can see, this plus cancels this minus and this plus cancels this minus. The overall charge is 0. The hydroxide group, the previous hydroxide group is, there are 2 of them. However, you can see now that there is only 1 solid hydroxide group and the other one is just forming hydrogen bond. Okay, it's same here. 1 hydrogen is lost because as you can see, 2 hydroxide are added and 2 waters are lost. So 1 hydrogen ion is lost. Okay, make sure you know this reaction and the color and its uses for qualitative and quantitative. Now in the next slide, we'll see how we can perform the quantitative analysis of nickel using DMG. This is the procedure. Okay. Since the only use of DMG is for nickel analysis, we also might want to understand the procedure. So basically you weigh the ammonium nickel. So ammonium nickel is the source of sulfate is source of nickel ion and dissolve it in water. Then you add HCl to make the solution acidic. Then you heat it to 70 to 80 degrees centigrade and add slight excess of DMG. Okay, and it would initiate the precipitate. So it will form the precipitation because we are forming that red powder. So avoid steam bath for, provide steam bath for 30 minutes. So basically you will be heating for 30 minutes. Then you cool the precipitate and filter it using crucible. So now you form the precipitates, you filter it. Okay, so that the PPT will stay as a residue and the left other things will go as a filtrate. Then the precipitate is dried at 110 degree to 100 to 110 degree. Okay, then you dry it and you weigh it. Once you weigh it, it is the 2 DMG and 1 nickel compound. So you can determine the mass of nickel in that compound which will be the mass of nickel in the initial solution. Okay, you see that? You form the precipitate. You form the precipitate which you dry, and then you weigh and do the calculation to get the mass of nickel. So there is some challenges. The precipitate generally has impurities that can be eliminated. Okay, so always there is going to be some interference. So if the impurities are iron or bismuth or aluminum, those with +3 charge, remember we are working with nickel 2 plus ion. So if there are other cations that are interfering the nickel 2 plus ion analysis, then for the one with +3 charge, you can add sodium tartarate. If you add sodium tartarate, then sodium tartarate will bind with these impurities and they will not react with DMG. Similarly, if there are other impurities with +2 charge, like cobalt, zinc, manganese, and magnesium, you can add sodium acetate to prevent their precipitation with nickel DMG complex. So for +3 charge, you use sodium tartrate, and +2 charge, you use sodium acetate. This is how you do it. Okay. So I have shown you in these 2 slides the uses of DMG for nickel analysis. Now, before we go into the next compound, let's see one of the research article. So this research article is using DMG for semi-quantitative mapping. Semi means partial quantitative. So this will not just give you exact value, however, it will give you a comparison. So it is like dark red, red, light red, no red. Okay, that is semi. Means it does not give you exact value, but it helps you to compare by looking at the intensity. Okay, so you are using DMG for the staining and for semi-quantitative mapping. Mapping means to show the nickel in plant tissues. Okay, you are using DMG to form nickel complex with the DMG, and that will help you to analyze the presence of nickel in different tissues in different plant tissues. Okay, here I have highlighted some of the sentences and some points that are useful for us. So first of all, this article was published in Environmental and Experimental Botany. So it is more toward the plant side. So we'll be just looking at it briefly, okay? And it was published in 2010 by several authors. They are from Switzerland, Germany, New Zealand, and Switzerland. So here is the abstract. On the abstract, there is determination of the nickel distribution in tissue of hyperaccumulated plant aids in understanding the strategies and mechanism used by these plants to take up nickel from soil. So basically what it is saying is you have nickel in the soil, and if you analyze the plant tissues, you can say how those nickels move from soil to the plant. It will help you to understand the mechanism used by these plants. Okay, so for that they are using this instrument ICP-OES, inductively coupled plasma optical emission spectroscopy, and this is one of the topics that we'll be discussing in the second part of this course. Okay, ICP, inductively coupled plasma. So the DMG method may be used in conjugation with the spectroscopic method to resolve biologically active nickel. So they are using this to form the complex with the DMG and using spectroscopy to resolve the biological active nickel. Okay, let's go into the introduction. And like I said, we'll be focusing on these highlighted results. Okay, plants that accumulate more than 100 milligram of trace elements per kg dry weight concentration, they're concentrating the element more in the shoot than in the roots, are called hyperaccumulators. So what is hyper? Hyper means more, or more, right? High. Accumulator means to accumulate, to store. So how much more? If it is more than 1000 milligram, which is more than 1 gram for 1 kg of dry weight of the plant. Okay, remember it is the dry weight. So first you remove all water and you weigh it and you do the analysis. If it is more, if the trace element means the element that are present in a small amount. If their quantity is more than 1 gram per 1 kg, then it is called hyperaccumulation. Okay, as the toxicity of the accumulated nickel must be controlled, hyperaccumulation comes at a metabolic cost for the plants, which would be avoided if the metal would be excluded from being taken off by the root and translocated into the shoot. Okay, basically this is the theory that if we can avoid the nickel mechanism, if nickel moving from one part to another, then we can control the presence of nickel in certain parts. Okay, so these are several. You can also find this paper and then study. Now let's move into the next. So here is the next part, which is DMG analysis, dimethyl glycoxime analysis. Okay, this is also one of the uses of DMG. You can try to understand. So element-specific staining techniques do not require expensive and complex equipment. So we know that DMG is element-specific, right? It is specific for nickel. So since this is very specific for nickel, it does not require other complex equipment. We can simply analyze it, or we can use cheap instrument to analyze it. Okay. So what are the other elements that are specific to other reagents? Here it's saying that lead in root stem and leaf tissue of various plant species using sodium rhodizonate. So as a staining agent, if you use this staining agent, then you can analyze lead. However, today we are focusing on nickel, okay, and DMG. So DMG is a staining agent particularly well suited for nickel. DMG forms a strong complex with nickel, as we have seen in previous slide, and the nickel DMG complex reflects and transmits red light. So earlier I showed you the picture of the red color. However, the range for that is, as you know, that every color has a nanometer range. For the visible, we can see it. The region is 600 to 450 nanometer. Okay, and this was reported by this article. This coloration can reveal the distribution of nickel in the tissue, right, as it can form the complex. So the interference may occur with cadmium copper, which also form red complex with DMG, and the color of the, so that means this there is some interfering agent, okay, like cadmium and copper. They also form complex with DMG, which is red color. The color of the latex complex, however, is less intense than that of the nickel DMG2. So these later complex, the cadmium and copper, their color is less intense and has less interference. That means it is not that big of a problem. Okay. So many investigators have used DMG for qualitative microscopic detection of nickel in plant. So these are several research articles. They have focused on using DMG as a qualitative analysis of nickel in plant tissues. Okay. As DMG is only sparingly soluble in water, ethanol containing solutions are often used. So they are using ethanol as a solvent. So ethanol was found to be enhance the penetration of some tissue by DMG, but also to destroy tissue structure and thus may contribute to nickel redistribution. So what they are saying is, so ethanol has the good properties. However, it also has some bad properties because they can destroy the tissue and they might help nickel to travel from one part of the plant to the another part of the plant, and it will give false information during chemical analysis. Okay, so what this is telling you is overall research is not that easy and there are several challenges. Okay, So the aim of this study is to develop a method that could be used to determine at least semi-quantitatively the distribution of nickel in hyperaccumulator plant as at tissue level. So they are doing this semi-quantitative because the quantitative just determining exactly how much is very difficult. So they are looking at how dark the color is. If it is very dark, it is more. If it is no dark, then it is absent. If it is medium dark, then it is medium present, like that, okay? In tissue level. So they are going into the tissue level. Now let's go into the next page. So I'm ignoring most of this part because we are just interested on some of them. So the calibration is one of the things that you have to understand to avoid color intensities into concentration. So basically you are getting the color intensity and you are converting that intensity into the concentration, okay? So first what you have to do, you have to calibrate it. Calibrate it means what this concentration of nickel ion will give you, what types of color, what intensity of the color will it give you. Then you form the, so this is showing you how the color are seen. So this is how you do. Then you plot those information and get the calibration plot. The calibration plot is also called standard curve or standard calibration curve. Now in this curve, see that the units are 10, 100, 1000, 10,000. On the x-axis, on the y-axis, it is 1, 10, 100,000. So the increment is on the basis of 10. If you see these types of graph, then it is saying it is on the log scale. It is also saying here, it is log scale. You can have only one log scale or on x-axis or log scale or y-axis. However, in this one, it is both log. X-axis also log scale and y-axis also log scale. Scientists like sometimes prefer log scale, or in several cases they prefer log scale, because if you do the linear scale, then the graph will be not this straight. It will be curvy and then it will be very difficult to predict. However, when you do it in the log scale, you can see the line is very straight and it is easier to analyze, okay, only for that purpose. And the calibration plot, the equation is y equals to 0.57 x to the power 0.6. The R square value shows you how good the data are related to each other. It is very, very good. 0.99 is very good. Okay. Like here you can see these pictures where they're looking at the colors and looking at the colors, okay, the different colors. And this is how the graph is, and then convert it into the picture. Okay, and this picture will show you the color. And they came up with the graph. So this is the summary graph. Okay, how the nickel is present, you can see that in this plot, dark color is for lips, and the other one is stem is very less dark gray color, and the root is medium dark with some stripes. So it shows that nickel is most of the time present higher in roots. Okay, in some cases they are present in between stem, and in most of the cases they are higher in all cases in leaves. In roots they are less, and in stems they are in medium. Okay, so like I said, we are just looking at the major part, and discussion is they are saying that using DMG to determine nickel distribution pattern in this root stem and this of the reproducible result. So it is satisfactory. You are getting good results. Okay, that is nickel is good. Conclusion. So at the end, using this DMG solution with pH of 10, they obtained consistent and reproducible DMG staining pattern of tissue sector of the nickel hyperaccumulator. So DMG is doing very good. They were able to stain the nickel. Okay. So at the end, the DMG staining method had the advantage that it gives a good spatial resolution, does not require expensive equipment, it is easy to use, and is rapid in comparison to other methods. So they're saying all good thing about DMG staining. Okay, that's it about DMG. Here we looked at the quantitative analysis, and in the other one, we looked at the semi-quantitative analysis. Okay, you can also find that article and then study it on your own. Now let's move on. Cupferron. So Cupferron is the another compound, the reagent that we have to understand. Ammonium salt of, so the Cupferron is the common name, okay, and its real name, the compound IPAC name is ammonium salt of N-nitroso N-phenyl hydroxyl amine. So ammonium salt. So the structure is given there. There are two structures and both of them reflects the same. The one on the right, let's look at it. Ammonium salt because it has NH4 plus. So it is like NH4 plus ammonium salt of N-nitroso. Here, N-nitroso and phenyl. So N-phenyl in this benzene ring, phenyl group attached to N hydroxyl amine. So this whole part is N-nitroso and phenyl hydroxyl amine, which is attached to ammonium group. So it is a salt of ammonium. Okay. So remember how to draw the structures. Its name is derived from the fact that the reagent precipitates both copper and iron. So it is called Cupferron. Why? Because it can precipitate both copper and iron, both of them. So Cop stands for copper and ferron stands for iron. So it precipitates iron completely in a strong mineral acid solution, and copper is only quantitatively precipitated in faint acid solution. So how it is used? It is used to precipitate the copper and iron. In strong mineral acid, it will precipitate iron. However, in the faint acid, it will precipitate copper. The selectivity of the reagent is greatest in strongly acidic solution. So if it is very strong, if it is strongly acidic, then it is better selective. Okay. So here Cupferron. It forms insoluble compounds with the number of metals in both weakly acidic and strongly acidic solution, mainly employed in strong acid solution, 5 to 10% of HCl or sulfuric acid, and precipitates iron, palladium, titanium 4, zirconium, cerium, Mb, TaW, all sorts of metals, and these elements also. These from these elements, okay? So metal cupferrates are soluble in diethyl etherate. So you form complex with cupferron, form complex with iron, for example, and that complex now you can, it will PPT, it will form a precipitate, and you can filter it, which you can, or you can recover it by soluble, making it soluble in diethyl ether, adding it to diethyl ether and in chloroform. Okay, so it has wide application in solvent extraction separation schemes. Thus, iron this may be extracted from hydrochloric acid solution by chloroform. So first, you form complex PPT with these reagents, and then you recover them by making them soluble in the other reagent. So precipitation is always carried out in cold since it decomposes into nitrobenzene on heating. So the cupferron, it decomposes into nitrobenzene if you heat. So you have to work in cold temperature. Like in DMG, we work in higher temperature though. So it is used in determination of uranium. Okay, it does not react with uranium-6, but it reacts with uranium-4, quantitatively precipitate. So these facts are utilized to separate iron, copper, titanium, and zirconium from uranium-6. So basically, if there is any uranium-6, then first you form PPT with the PPT of these ions with Cupferron, and uranium-6 will not form. Okay. Then these, once they form PPT, they can be recovered by using the solvent like diethyl ether and chloroform. Okay. After precipitation of this in acidic solution with Cupferron, the uranium filter is reduced to uranium-4. So you separate uranium-6 from others, and now you convert this uranium-6 into uranium-4, and then precipitate with Cupferron. Ignition of the uranium-4 Cupferron complex gives U3O8. Okay, that is used in uranium. Now, let's look into Cupferron. Okay, so this is the website. It's chemicalbook.com, and here I have searched Cupferron. See what kind of information we get. So, like if you want to know more, then this is the structure of the Cupferron, like I've showed in the PowerPoint slide. So the chemical name is Cupferron. The chemicals, they have this number. This is the unique number, like your student ID number, that is used to identify this compound. Okay, its formula weight is 155.15, and its molecular formula is C6H9N3O2. Cupferron properties: melting point, boiling point, density, refractive index, everything is given. Okay. Safety issue: it is very dangerous. That's what it says here. Oops, sorry. Let's see some other information I missed. So it is. There are several manufacturers: Sigma Aldrich, TCI Chemical, and Alpha Azer, with the product name this. The same company, but different mass. So if you are purchasing 100 gram, then it will cost you $205. Okay. So like in a straight way, 1 gram will cost you $2. Here it will cost you 25 gram will cost you $30. Alpha Azer. Okay. Remember that this is the price. However, there is also some shipping cost associated with it. That means you have to pay extra for delivery. $2 per gram is not that expensive. Usually 1 gram, $1 is very cheap. So 2 is not bad. Okay. So chemical properties: it's a very important analytical reagent. As ammonium salt of this, commonly known as Cupferron, it is usually white, yellow, bright flake crystal with sweet odor. Okay. The reagent is thermally decomposed into nitrobenzene. That's why we should not heat it. It is unstable in light and air. So if you have it, then you have to avoid light and air. Okay, that's why we store it in the brown reagent bottle. Okay. Now let's see purification method. If there is some impurities, then you can purify. The method is given here as well. Chemical properties: uses. So Cupferron is used for quantitative analysis of aluminum, zinc, copper, iron, gallium, mercury, manganese, this, and other elements. It is used in polymerization in vitro due to unique polymerization in vitro characteristic of Cupferron. Also, amounts in small can be used as an alternative of phenol polymerization into PST, which is currently largely applicable. Cupferron is used for colorimetric determination of the weight of aluminum, bismuth, copper, iron, mercury, and all these ions. Okay. Production method is also given here. Category: toxicity, it is highly toxic. So basically, I'm trying to show you is how to find the information. Okay, and for us, the important part is this uses. Okay, now let's move into the slide. Cupferron. Okay, now we are going into oxide. So the last topic is oxide, and oxide is the common name is oxide, and the real name is IPAC name is 8-hydroxyquinoline. So if you want to study the book, then it is in the book there. It is available in different places. In Vogel, page number, either it's in page number 441 or 469, depending on which book or what pattern you have used. Like in PDF, the page number could be 441 in the real book. However, in the PDF, it will be different page. So one of these, and it is in two different places. The first one is in 441 range, and the other one is 407 range. Okay, and also I'll be first showing you the journal article, and then I'll go into the book part. Okay. So this is the Research and Review Journal of Chemistry. So this is the review articles. So review article means uh, the people who are uh, who wrote this article, this review, um, they are just collecting the information from other authors, other published journal, and they are kind of summarizing it. They're trying to show how this hydroxyquinoline and its derivative, how it is synthesized, and what are their applications. Okay, how people have used it in different ways. What are the different ways that you have used? So this kind of article is very helpful, because now we want to know about 8-hydroxyquinoline. We cannot go to every article and read how it is used. So people have read all those articles and they have summarized it here in very good manner, scientific way, so that we can read them. And if we find any of those application or synthesis helpful, then we can go to that paper and study in depth. Okay. So studies of structure, chemical and synthetic aspect of 8-hydroxyquinoline, which is also called 8HQ, and its derivatives mean you have 8HQ, 8-hydroxyquinoline, and the compound derived from 8-hydroxyquinoline. Okay. Introduction. 8-hydroxyquinoline is one of the most popular and versatile organic compound. It is an organic crystalline material that made up of two rings. So we haven't seen the structure yet, but it says that it has two rings. One ring is phenol, that is fused, that means connected, or the part is shared with pyridine ring. So you have two rings, one is phenol ring and pyridine ring. Phenol ring means benzene with hydroxide group, and pyridine is benzene where one carbon is replaced with nitrogen. Okay, 8-hydroxyquinoline and its derivative have found a great varieties of application, ranging from pharmacological and pharmaceutical agent to electron carrier in organic light emitting diode, OLED, and fluorescent chemical sensor for metal ion. Okay, 8-hydroxyquinoline reagents ligands has been applied for analytical purpose and separation techniques. It is an excellent reagent for gravimetric analysis, and it can be used for extraction of metal ion. So this is more important for us. So the 8-hydroxyquinoline is used in extraction of metal ion. Okay, and that is useful for the topic that we are discussing now, using gravimetric analysis. Gravimetric means, like we did it in nickel DMG, you separate the compound and then you weight gravity, you get the information about the weight structure of 8-hydroxyquinoline or 8HQ. So this is the structure. On the left is the 8-hydroxyquinoline, and the structure number 2 is the quinoline. So this is quinoline, and to put the 8-hydroxyquinoline, you put hydroxide group on the 8th position, okay, counting from nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. So in the 8th position, you have hydroxide group. So the ring with 5, 6, 7, 8, that is phenol, okay. Remember, these 2 carbon are shared by both ring, that is fused. These are fused ring. They are saying sharing the part. And the second, the right side with the nitrogen in it is the pyridine, okay. So it is the fused between phenol and pyridine, and the phenol hydroxide group is in 8th position. So this structure, the one, the hydroxide hydrogen can be donated to amine nitrogen, because the nitrogen has lone pair, it is a base. It can abstract that hydrogen to form this deuterion. Deuterion means 2 ions in same compound, okay. For some reason this is O minus, however I think this should be H plus. In deuterions you have both positive and negative ions, okay. So as a result of proximity of the hydroxide group, so that means hydroxide and nitrogen are close to each other, form insoluble chelate compound complex with a great varieties of metals. So this is how it forms the complex ion. So this is again complex symmetric types, okay. So the metal ion that can form 4 bond requires 2 hydroxyquinoline, okay, and both oxygen and nitrogens are forming the covalent bond with metal ion. Similarly, if they are forming 6 covalent bonding metal, then you require 3 of the 8HQ. As you can see here, 6 of them require 3. It's like 6 covalent metal complex require 3, and 4 covalent complex metal require 2 DMG. And what are those metal? Copper, bismuth, manganese, magnesium, iron, aluminum, zinc, and nickel. Okay, these are these reagents. And like I said earlier, they are getting the information from other source. What is the source? It is number 3 that you can find in the reference, okay. So this is how the complex is formed. Synthesis, we are not focusing on the synthesis, however, we'll just look into one equation. So this is how it can be synthesized, okay, from this compound 6. So the compound 6 is 8-aminoquinoline, okay. You are converting this NH2 into OH group, or you can convert this sulfonic acid group into OH group, okay, using these two. So the most used method in the category is Suzuki coupling, cross coupling. I just highlighted it because Suzuki cross coupling is a Nobel Prize winning coupling reaction. So it has shown how can you prepare different derivatives of 8-hydroxyquinoline, okay. So now we are going into the application. So 8-hydroxyquinoline, it can be used as fungicide and insecticides, okay. You can use it as an insecticide. It's a potent lipophilic metal chelator whose 8-hydroquinoline copper chelate is used extensively as fungicide. So this copper chelate is used as a fungicide in several countries to control the disease of freckles, scab, and black spot in cucumbers. In different fruit, you can use this as a fungicide, okay, to kill fungus. And also you can use the other derivatives. These are the derivatives of 8HQ as an antifungal agent, okay. So you can see the compound of Cupferron, compound of 8-hydroxyquinoline can be used as a fungicide, okay. it can also be, the derivatives can also be used as anti-insecticides to kill the insects, and fungicides. So these are the derivatives of 8HQ. They can be used as a fungicides, anti-insecticides or anti-fungicides. Okay. It can be used as a, the derivatives can also have a antibacterial properties to kill the bacteria. So these derivatives are used to kill the bacteria. Anti-tumor and anti-HIV activities. They can be used as an anti-tumor or anti-HIV activities also, the derivatives. Okay, not all of them, but these derivatives. It's on here. I'm just trying to show you that it has several uses. Okay. Anti-neurodegenerative properties. So these are the derivatives of 8-hydroxyquinone. They have these properties. Okay, now we are not focusing on the other part, and these derivatives can be used as aluminum chemosensor. So you basically develop a sensor that can be used to sense the aluminum. Okay, so in conclusion, due to the unique chemical properties of hydroxyquinone and its derivative, many of these compounds nowadays have application in medical, as you have seen in fungus, antifungal, antibacterial properties, OLEDs, agriculture. Okay, you have seen those, chemosensor, and metal extraction properties. Okay, so this article, it reviewed different aspects of 8HQ and its derivatives, including their synthesis and application. Okay, that's good. Now let's go into the book. So this is the part of the book, Vogel. Okay, Vogel's quantitative analysis, and this is page number 407 of that book. Okay, so determination of metal by means of 8-hydroxyquinone. So 8-hydroxyquinone is also called oxide. Okay, so this is showing you how you can use this reagent for determination of metal. So it is saying that various metals like aluminum, iron, copper, zinc, cadmium, nickel can be, under a specific condition of pH, well-defined crystal precipitate with 8-hydroxyquinone. This PPT have general formula of this. Okay, this is 8-hydroxyquinone with the metal and N for the charge on the metal. Upon treatment of the oxygenate with the dilute HCl, now you form this complex. You can treat it with dilute HCl to liberate the oxide. So it gives you back the oxide, and one molecule of oxide reacts with 2 molecules of bromine to give this. So you are using bromine to form this compound, and like it is also one of the uses of bromide, right? Bromate that I have discussed in past, that you use to liberate the bromine, that can be now used here to determine what how much this oxide or 8-hydroxyquinone is bounded with metal, and it will help you to determine the amount of metal. Okay, see, you can do all the studies on how it is showing you determination of aluminum, how to do it. Okay, read the book and figure it out. Okay. Okay, like I said, it is mostly theory. It is more reading than me guiding it in few minutes or in a couple hours. So today we discussed about DMG, we discussed about Cupferron, and we discussed about 8-hydroxyquinone. We also looked at how we can find different information using internet, book, and journal articles. That is today, it is also the end of the part 1. So I have summarized some of the important questions. So these are some of the important questions that I feel are important for this part 1. Okay, so like I said, these are only sample questions. Please don't rely on this question only for your exam preparation. Okay, like there are other possible questions also. However, I thought these are these are types of question looking into the syllabus and past question. Okay, so basically what kind of questions you are expecting? You are expecting the definition, like what is redox titration, what is complex symmetric titration, what is precipitation titration, definition. Okay, make sure you know the definition. And for similarly, you need to know about the indicator. So you need to know the characteristics. What are the main characteristics? Okay, for redox indicator, complex symmetric indicator, and precipitation indicator. On precipitation indicator, you should focus on adsorption indicator. Okay, even though in exam it doesn't tell you, that's where you have to focus. So one part is characteristics of indicator. The second part is definition and mechanism of the indicator, like how it works. The first part is what are the properties of the indicator, and the second part is how does the indicator work. Okay, you have to write the mechanism, the formula before, after, how the color change, what, like why the color change, those kind of answers. Mechanism. Okay, then after that you also need to know the principle of titration, like the principle of redox titration, principle of complex symmetric titration, principle of adsorption titration, or precipitation titration. Okay, so principle of redox titration is there should be change in oxidation or number, and you use the indicator to determine the equivalent point, and once you determine the equivalent point, you can determine the concentration of analyte. Make sure you provide the example of the indicator, you provide the example of on how it can be used, its change in color and all those things. Okay, for all these three principles. Okay, so the first is, again, we are focused on three types of titration: redox, complex symmetry, and precipitation. So the first part is characteristics of indicator, second part is mechanism of indicator, and the third part is principle of titration. Different types of titration. Okay, the answer is very same, however you have to focus on what the question is asking for. Now we go to question number 10. So the question number 10, 11, 12 are general question based on each topic. So in redox titration, you should know what is formal potential. Okay. In complex symmetric titration, you should know the role of metal ion indicator. You know that. How does it is like a principle and all, like the combined form of everything. And the third is, how does the adsorption indicator indicate the end point in precipitation titration. This is very similar to what is the mechanism of adsorption indicator. Same thing. Okay. Now from question number 13 onward, these are all significance of different chemical reagents that we studied. Potassium bromate, okay, EDTA, Cupferron, Oxide, ferric salt. I have missed DMG. Here is DMG. All of these. Okay, so DMG, Oxide is also 8-hydroxyquinoline. Cupferron are organic. Ferric salt and potassium bromate is inorganic. EDTA is organic, however, it came as a part of complex symmetric titration. Okay, so for these reagents, make sure you know their formula, specifically what they are used for, the reaction. Okay, what types of titration they are used for. For example, potassium bromate is used for redox titration. EDTA is for complex symmetric. Cupferron and all these. Okay, similarly, all these, you know exactly what they are used for, what types of titration, because our course is focused on titration on. Okay, KBRO3, what it is used for, all those things. Okay, with that, I would like to end this section, and we'll see you in next and lecture 5. That will be part 2 of this series. So we are done with the part 1. With that, thank you.